Hi, my name is James Warren and I'm here to do a presentation to tell you about the T-duality of closed strings, and today specifically sigma, which is a very useful parameter used in string theory. So just a little recap. Here's our two-dimensional model here. We have the curled dimension gamma, which is curled up in the x dimension. We came across this equation where the energy of free strings equals an integer n over r, where r is the radius of dimension gamma. And we also came across the idea that strings could be wrapped, and therefore they'd have tension. And wrapping number was denoted the mathematical symbol m. And from this diagram we can see if the strings go up, have upward arrows, we can think of them having a wrapping number of m equals +1, and downward arrows is m equals -1, and no arrows at all is m equals 0. And also that wrapping number was conserved, and we came across this formula where the energy of a wound string equals the wrapping number m times by the radius of dimension gamma. So, what is sigma? Well, sigma is just a way of naming parts of the string, and it goes from 0 to 2 pi. But are you still confused.com? Well, here's an example for you. We're going to think of a string as an elastic band. And elastic bands are made out of lots and lots of molecules, or lots and lots and lots of sets of atoms just strung together in a long line. And we could name each of these sets of atoms, or monomers if you're a chemist. We can give a certain name with respect to pi. So here we've got 0 pi, 0.1 pi, 0.2 pi, etc. And for closed strings, like elastic bands, once you get to 2 pi, you'll go back to 0. So go 1.90 pi. So 1.9 pi is 0 pi. That's the way it would work. So the energy of free strings can be denoted this formula, the integral of d gamma by d tau, where gamma is dimension gamma, and tau is the time variable that describes the motion of the string. And it's a bit like velocity if you think about it, where gamma is the distance and tau is the time. It's a bit like that. Now, for wrapped strings we're given this equation. M equals 1 over r times the integral of d gamma by d sigma. And that leaves us with the equation the energy of a string equals d gamma by d sigma. And that leaves us with the equation where the energy of the wound string is d gamma by d sigma. Right, so we have this equation. The energy of wrapped strings equals the integral of d gamma by d sigma. Now, let's have a look to see if that is sensible. If we have our dimensions here, x and gamma, and we draw a string. Now this string isn't like the strings that we've been drawing. This is a sort of a real string, if you like, but it has a weird shape as it comes round this around dimension gamma here. So if we think of it as if it was a normal elastic band. We could plot a energy versus sigma diagram, and we could also plot a gamma versus sigma diagram here. So if we redraw in our string, like so, we can say, okay, well, when it's going vertically, we know that the string is tight, and therefore will have a high energy. Whereas when the string, the string is horizontal, it will have a low energy because it's not actually stretched. So we can have a look at this, and then we can plot a diagram, and we get something like this. Say this was just a normal rounded bit, and so was this bit. We're only going to focus on this bit. We'd have an energy that looks something like this. The energy of the string will be constant, but then it would suddenly drop down, and then it would go up again. Or, if we looked at the sum of the energies, then it would sort of go up like this, and then it would go across, and then it would go up again. This is forgetting that this bit here exists. There would be a little mound in there, and on this diagram it would go flat, then it would go up, then it would go flat again. But anyway, if we look at the gamma by d sigma, remember sigma's changing all the way along here, going from 0 to 2 pi. So when something is on a horizontal line like that, we're getting no gamma, but sigma is still increasing. So we in fact get something, again, which is like that, which, as we saw over here with the sum of the energies, was exactly the same shape that we got. And so this is basically showing us that the energy dWt by d sigma could in some way be related by d gamma by d sigma, or the energy is related to d gamma by d sigma, which is the equation we have up here. The sum of d gamma by d sigma is the energy. So a thing to notice here is we've got interchanging n and m, interchanging r and 1 over r, and interchanging d gamma by d tau and d gamma by d sigma. But how is this useful? Well, if you go through string theory and swap all the d gamma by d taus for d gamma by d sigmas, string theory will produce exactly the same predictions as the previous string theory predicted. And if anyone says that's not a useful property, well, let's just say they're wrong. Thank you very much for watching my presentations, and check out the links page. I've got a lot of links there about string theory and T-Duality, etc. And thanks a lot. Bye.